hours. That would be exciting math. Yeah, that would be painful. Okay, there we go. All right, so on last Thursday, yes, it was last Thursday. Last Thursday, we talked about properties of exponents. So how we can multiply terms with exponents, divide terms. What do we do if we have an exponent to an exponent? All that good stuff. So that was last week's recording. And then we decided I decided that we were going to skip over 5.2. And we started in 5.3. So we talked about adding and subtracting polynomials together. So polynomial is just a fancy way of saying a monomial is just one term. A binomial is two terms. A polynomial just means more than that, more than two terms, basically. We have these polynomials that we're adding and subtracting together. And I know we'll just do one just to kind of refresh our brains and then jump into multiplying polynomials. Guess I don't need all that. I just need this. There we go. So these aren't too bad. I think that you've probably done adding and subtracting polynomials for a while. I know in Algebra 1, we do a lot of them. The biggest thing with adding and subtracting polynomials, well, there's two things. One is that you have to make sure that the term, so when I talk about a term, it's basically one of these. In this first polynomial, there's 4 terms right there. So it's just that one little part that's in between the addition or subtraction sign, that's a term. So when you're adding or subtracting terms, you have to make sure that you add or subtract like terms. So the word like terms means that you're basically looking at the variable and you're seeing if the variable matches up to the other variable to see if you can add or subtract it or not. So that's number one. The second thing is if you're adding two polynomials together, it's easy peasy. If you're subtracting, you just have to remember when you see this subtraction sign that it applies to everything in the second polynomial. So that's the biggest thing that I see people get tripped up on more than like terms, is that they just want to subtract. In this example, they just want to subtract the 3v cubed, but you're actually subtracting 3v cubed, you're subtracting negative 12v squared, and you're subtracting 8v. So that's kind of the two biggest things to watch out for. Other than that, it's pretty easy peasy. So if I want to subtract these two polynomials from each other, I'm going to simplify. And if you want to try this on your paper too as I'm doing it, that's fine too, just to... You got it. Okay, so the first polynomial stays the same, no big deal. The second polynomial, we have to read that negative sign. So we're going to subtract 3v cubed, if I can read really small. We're going to also subtract a negative 12v squared, or we're subtracting 12. So when that's the same as adding 12v squared. Okay, that's because really, if you would look at it, this is minus a minus 12v squared is what that is. V squared. Okay, and then we are going to subtract 8v. Because again, the subtraction, it's plus 8v, but we're subtracting the whole polynomial, so we have to put the minus sign to the 8v as well. So that was the first watch out. I was talking about that. And then the second one is just matching up like terms. So we have one term that is a v to the 4th power. We have one term that is a v to the 3rd power. This v squared and v squared match up. We have a v here and a v here that match up, 4 all by itself. So then when I combine, 8v to the fourth has no other like terms, so that just stays the same. 8v to the fourth. Or minus 3v cubed. Okay. And then we have 2v squared terms. So it's 12v squared plus negative 2v squared, so plus 10v squared. And then our v terms, we have a plus v and a minus 8v, so minus 7v minus 4. And this would be our simplified polynomial. Now, when people get here, a lot of times they get nervous because it's like, ooh, that doesn't look very simple. There's like 5 different terms there. But that is as simple as it gets because we cannot combine v to the fourth and v to the third in any way. The only thing that we could possibly do if we didn't have this last 4 here would be to pull a v out of all those terms, but we still can't add or subtract them together. I mentioned this on the last time, but I do think it's worth mentioning it again because I think it helps us remember why we do it. The reason, for example, that you can add, let's take these two guys together. The reason that you can combine negative 2v squared, 12v squared, is because they share v squared in common. Pull out v squared out of both of those, v squared, we're left with negative 2 plus positive 12. Negative 2 plus positive 12 is 10, 10 v squared. So that's how we come up with this 10v squared. We don't do this every time because we've just learned over time that if you have like terms, you can just add the coefficients. Actually doing when you add the coefficients. All right, so that was a review of last week. The new stuff that we're going to do is multiply polynomials. Woohoo, right? Okay, so this goes from easy multiplying to more complicated multiplying. So we'll take the first two, which are the easy ones. Well, we'll take them all, but we'll take the first two. And then 6 and 7 are a little more complicated. Okay, so number 4 is a pretty straightforward multiplying polynomials together. You'll see you have x times 2x squared minus 5x plus 7. And you'll notice the second polynomial string is inside parentheses. So whenever anything is inside parentheses, in order to break it free, we have to get rid of whatever is multiplying or whatever is happening to the parenthesis. So in this case, x is multiplying everything that's inside the parentheses. This is a pretty easy one because in order to get rid of the parentheses here, we're going to use my favorite property, which is the distributive property. And that means that we need to multiply every term inside the parentheses by x. So if this was, instead of x, if it was a negative sign, like in subtraction, right, then we would need to distribute it to everything inside the parentheses. Also works the same exact way. So this is going to be an easy one. We have x times 2x squared, which is going to give us 2x cubed. And then we have x times negative 5x, which is going to give us negative 5x squared. And x times 7 is plus 7x. So that's all we have to do for number 4. It'd be nice if all of our homework problems were like that, right? Okay. 5. Connor, do you remember what we had to do to 5? Has it been ingrained in your brain from Algebra 1? I'll give you a hint. It starts with F and ends in oil. Yes. Yes. It's in there, right? Stuck in the brain. Yes. So when I see this, when I see it, 2 binomials, that technically this is 2 binomials that are getting multiplied together, but basically you have two sets of parentheses with 2 terms in each thing. then alarm bells should go off in your brain, FOIL, FOIL, FOIL. Now, every time I teach this, every year I do Algebra 2, when I get to this one, people are like, oh yeah, FOIL. Like, I don't know, it just, once you're reminded, you're like, I remember how to do that. But sometimes just seeing it, after not seeing it for a while, it's like, huh, how do I do that again? If you do completely forget FOIL, you could actually use the distributive property and it would work. And by that is you could distribute y minus 7 to each of the terms in here. And then you would have to basically distribute and distribute again. So what FOIL does is it's just a shortcut of the distributive property is really what it is. And I could show you what that looks like, but it's just kind of long. It's just, again, you distribute and you have to distribute again and simplify, and you're going to end up in the same spot as FOIL. But since I know, I'm sure, Connor, you've done FOIL, and I'm sure the people that are watching the recording have done FOIL, we're going to just go ahead and use FOIL. Because if we have the tool, we might as well use it. So FOIL, remember, stands for that we're going to multiply our first terms, our outside terms, our inside terms, and our last terms. So just to kind of give everybody a review, our first terms would be y times y. So that's y squared. Okay. Our outside terms are going to be y times 6, and it's positive, so plus 6y. Our inside terms are negative 7 and y, so negative 7y. And our last terms are negative 7 times positive 6, so negative 2. Okay, so then we have to combine our outside and inside. Well, usually we get to combine our outside and inside, and we end up with y squared minus y minus 42. Not 14, 42. So that's our good friend FOIL. We like FOIL, right? The alternative is not as fun. All right, I'm looking at the homework here. 3 through 21. Okay. Let me pull up my book. Just make sure I'm covering everything. Three through 21. Okay, yeah. So pretty easy stuff in the homework to be able to do this. I say, since you're on the call, let's do 21 together, because that's basically what is happening in example 6 and 7. So let's do 21 together. And I'll write it up on the screen if you don't have it. So 21 is, oh, I'm going to color code it, because why not? 2a minus 3 times a squared, a really big A, minus 10a minus 2. There we go. All right, so if I want to, basically they're asking me to find the product of the polynomials. Okay, so they're asking me to simplify. Unfortunately, I cannot use FOIL to simplify, because I would really, really like to use FOIL because it makes things easier. So what I'm going to have to do in order to simplify is that I'm going to have to take this green, it's actually a binomial, take this green binomial, and I'm going to have to distribute it to every term inside my purple polynomial. So what I mean by that is, for a squared, it's going to be a squared times 2a minus 3. And then I have minus 10a times 2a minus 3. And then I have my last term, which is minus 2 times 2a minus 3. So I have to distribute this first, the first binomial, the first polynomial, to each term in the second polynomial. Technically, I could distribute the opposite way too. So if you really want to, distribute the other way, you could do that as well. It would work either way. So what you end up with is a big mess, first of all, and you end up with a expression that needs to be simplified even more by using the distributive property again. So you can see now we have each of these terms is multiplied by a binomial. And in order to get rid of the parentheses in the binomial, then we have to distribute the first terms in here. Okay, so a squared times 2a, this first term, is 2a cubed. Then I have a squared times -3, so minus 3a squared. Okay, this is where it gets a little more tricky. Our second term is -10a, so you want to make sure that you take the negative sign when you're distributing it. Okay, so this is going to be -10a times 2a, so you're going to get -20a squared. And then we have -10a times -3, so positive 30a. And then our last term, again, we have a subtraction, so we're going to carry that subtraction to make that the -2. So we want to distribute that to each, so we're going to get -4a plus 6. So -2 times 2a is -4, and -2 times -3 is positive 6. So then once we get here, we get to practice our adding and subtracting polynomials together, right? We have an a cubed, that's the only one. So 2a cubed stays by itself. Then we have -3a squared and -20a squared. So that's -23a squared. We have a positive 30a and a -4a. So that would give me 26a plus 6. And these always crack me up because I feel like what you end up with as answer is never as simple as what you start with. But they're two different ways of writing the same exact thing. So that is that. Make sense? Does that work, Connor? All right, cool. So as long as you can do number 21, everything else should be cake. Should be easy. All right, I'm going to do a little bit of chapter 6, and then I'll let you head on your way. And the people that are watching later head on their way as well. So that's it for chapter 5. It's 2 sections. It's very, very complicated that we're going to cover in chapter 5. 2 sections. Okay. So 6.1 actually is a, I think it's a really interesting section. I don't love my notes for it, so I'm going to go off script a little bit here. But actually a really useful section and something that I don't think people usually cover till Algebra 2, but I'm like, I think we should cover it a little bit earlier because I think, oh, yeah, that helps out a lot. All right, so what am I talking about? I'm talking about square roots and higher order roots. So we spend a lot of time, I know my son's doing pre-algebra, so he's doing a ton of stuff with square roots and simplifying it and all that good stuff. And we learn about square roots, and if we have the square root of 64, we know that's the same as 64 is 8 squared. And since we're taking the square root of 8 squared, we know that the square root of 64 equals 8. Okay. And we call it the square root, right? And so we can also take things like the cube root or the fourth root. We can take higher order roots as well. So one of the interesting things about square roots that I don't think is usually covered is that there is a different way of writing the square root, and that is if you have the square root of some number a, you can also write that as a to the 1/2 power. So it's kind of weird, not something that we always use, but it actually is helpful when you're trying to evaluate equations with exponents and move exponents around. So just to kind of prove that it's true. Have you seen that before, Connor? Okay. Okay. Demos. Just to kind of prove it's true. If it opens. All right, so if I have, obviously we know what the square root of 64 is, but if I do 64 to the 1/2 power, I also get 8. Just another way of evaluating that. And then the same follows for cube roots. So a cube root, I don't know if Desmos has a pretty way to write that. Oh, here we go. So a cube root is when you have a little 3 here, that means a cubic. So let's see, 64 is not a perfect, yeah, 64. All right, so if I take the cube root of 64, I get 4. Okay, so that basically means 4 cubed equals 64. Or I could write that as 64 to the, nope, to the 1/3 power. Another way to write it. So it's not like, you know, crazy mind chattering or anything like that, but it does become helpful, especially in Algebra 2, when you're trying to move exponents around and you're trying to maybe multiply two exponents together. If you have a square root sign, then a lot of times you can think of it as, instead you can think of it as being part of a fraction, or having a fraction exponent is what I meant to say. Yes, so that's that. I'm looking at my little chart here, and I don't like my little, like I said, I don't like my notes here because I don't think that they're clear. So what this little table refers to is if you are taking the square root of a number b, okay, to some n power. So this little table says basically you're taking the root of b and it's some number here. So if this number n is an even number, so the square root 2 is an even number, right? You're taking the 4th root of a number. So if you take the square root or the 4th root or the 6th root of a number, okay, and this number in here is greater than 0, then you're going to have 2 real roots. Okay, so what I mean by that is that, and one is the principal root. So if I take the square root of 64, right, the principal root is going to be 8. But there's also a real root at -8 because -8 squared is also 64. So there's 2 real roots when you have that. If the number inside here, the b, is less than 0, okay, so it's less than 0, then we get into the situation where we have to use an imaginary number, so we don't have any real roots, okay? And then if the number inside here is 0, there's only 1 real root. Now, that's if this number up here is like a 2 or a 4, if it's an even number. Now, if this number here is an odd number, like 3 or 5, then if b is positive or negative, we have 1 real root. And that's due to the fact that, like if I have, for example, -4 cubed, right? -4 cubed can give me positive 64. But there's no way that, there's no way I can get a negative value when I do something to the fourth power. So the reason that we have a real root, even when this number in here is negative, is because of the ability to multiply it an odd number of times. I hope I'm explaining that right. Okay, so that's what this little chart's about. It's not like you have to memorize that, but that's just kind of a thing to know. The other thing that I should have mentioned straight off is that when you have just the square root of a number, some number x, this is implied that this is the square root and that the number here is 2. We kind of say it when we say, well, we say square root, but it's an implied 2 right there, that we're taking the square root. Anything else is going to be labeled the cube root, the fourth root, all that kind of thing. All right, so that's just a little bit about square roots. The other kind of a little bit more complicated thing is down here at the bottom of the notes. And this is if we have it's right here. If we have I always forget to go back here. If we have a to the mn power, so we have some, let's do some real numbers here. We have 4 to the 3 over 2 power. It's kind of weird when we see like that. That can be evaluated as a square root. So if we kind of break this apart, and we're going to talk about the properties of exponents in a little bit, but we could rewrite this as a to the m times a to the 1 over n. And when we have 1 over n, we know that this is the same as the square root, or the nth root of a. So since we have that, then we can actually pull that out and say that this is to the m power. So you can see the property down here. If you have a to the m over n, you can rewrite that as the nth root of a to the m power. That one is not quite as, I don't know, useful to use all the time, but it's also just something to kind of note. Okay, so let's just do a couple examples of these, and then I think we should be good for the day. It should give us a good head start heading into Monday when we're back. All right. Again, I don't love my notes for this, so I have to kind of paraphrase in what's going on. So these first two are basically saying evaluate the square root is what we're asking to do. Okay, so we have our root is 3. So we're taking the cube root of negative 216. Okay, so if we wanted to evaluate that, there's a couple ways we can do it. The easiest way, honestly, is that we are going to use our calculator. Okay, so in your calculator, pull up Desmos. And there is a function under functions, under miscellaneous. There's a root with a little n. So the n indicates what root. So we're taking the cube root of negative 216. So then all you do is plug it in and you see that, okay, that's negative 6. If you have a calculator like on your phone that you can't do that, you could type in negative 216 to the 1/3 power, because that means the same thing. If you really have an old calculator, it's like the basic calculator, and you can't type in 1/3, so you could do negative 216, and then you just know that 1/3 is like 0.333, so just type in, I didn't like that. Weird. Okay, so apparently you can't do that. Maybe Desmos doesn't like that. Um, to the 0.3. Okay, so Desmos doesn't like it when you put in 0.33333, even though that represents 1/3. I think if you do it on like your phone calculator, it'll probably let you do it because it's not as picky about things. All right, so that it's totally valid to use the calculator to do that. Just kind of evaluate to see that you know how to punch in the numbers there. So that's for 1 and 2. Number 3, actually, when you get to kind of the middle part of your homework, it says evaluate the expression without using a calculator. So that's in 20 through 31, and I don't even know what's on your homework. So, 20 through 45. Yeah, there's a lot in there. I have calculator in parentheses. I'm not like you can't use your calculator ever. However, I do think that you should be able to look at some of these and make an educated guess about what's going on. So what do I mean by that? Like, for example, number 3 on your paper has 25 cubed, no, 25 to the 3/2 power. Okay. So I know that another way that I could write this is 5 to the 2nd root cubed, because we just kind of talked about that property. So I know the square root of 25, that's the easy one, is 5. 5 cubed is 5 times 5 times another 5, so 125. So could I type in 25 to the 3/2 power? Yes, and get 125. But it's also something that we should be able to at least kind of figure out exactly what's going on. Like, not, just kind of using our common sense and, standard terminology, I guess. So then number 4 is the cube root of negative 125. So this looks really familiar, right? This negative 125, and I just saw that 5 cubed equals negative 125. So then I would guess that the cubed root would be 5. And actually, I'm like, is that 5 or negative 5? I'm thinking for a minute here. I think it's negative 2. Yeah, it's negative. It's negative 5. And Connor, it's negative 5, right? Because get negative 125 inside my radical, I have to do negative 5 times negative 5 times negative 5. These two are going to become positive, but then I'm going to end up with my negative 125. Yeah. Let's talk ourselves into that. That sounds good. No, I think that is the correct answer. It's negative. And then a little bit more fancy, but still not anything too crazy. If you get to like number 5, example number 5, we have x cubed equals 64, and we want to solve that. Well, before, if we had like x squared equals 64, we would just take the square root of both sides, and then it's plus or minus, so we know that x could be plus or minus 8. But when we want to take the cube root, or when we have x cubed, we want to take the cube root, right? So we would take the cube root of one side, and you would take the cube root of the other side. And then we would end up with, what do we say? 4. Yeah, because 4 cubed is 64. So it's really pretty easy. I think it's just kind of a good introduction to that. What we'll use it for, just to kind of give you a heads up, is that we're working with different kinds of roots here and different like fractions that are in the exponents. And then on Monday, we'll talk about all these different properties that you can do with exponents. So you can see here, for example, if you have 6 to the 2/3 power raised to the 1/2 power, we can actually simplify that using properties and radicals and all that fun stuff. So that's kind of where we're going with it. But I think that is good for today, unless you had any other questions. All right, that sounds good. Well, let me turn this off.